Okay, hello. There is no audience in here, but since I have said that I'm going to make a summary of the this week's lectures, I'm going to proceed without any audience, right? So let me remember what we have actually said in the last week. So we have essentially talked about the two-dimensional rotational group, the orthogonal group O2, right? So I'm just going to go up a little bit. So we have actually seen that there are these two kinds of elements in there. So what we call as the proper rotations. So these are elements that have determinants. I mean, these are matrices where the determinant is +1. These are actually rotations by an angle theta. I don't know if I have it. Yeah, it's a picture like that, yes. So the x-axis is transformed like that, and y-axis is transformed like this. So these are elements that can also be obtained by successive applications of small rotations, and so on. And then we have the reflections. These are obtained, yeah, whatever. And these have this general expression. They have the property that their determinant is equal to -1. So in that case, they can be considered as a reflection across some kind of a line. So there's, I think the picture is somewhere in here. There's something called a mirror plane in 3 dimensions, but mirror line in 2 dimensions, actually. We're essentially taking the mirror reflection of any vector in here. So if I have a vector somewhere in here where that angle is alpha, so that vector is going to be transformed into this vector where that angle would be alpha, right? You can actually think of it like that. Okay. In any case, so these are the basic transformation types in here. And then the next question is like, what's a finite subgroup? So this is important because, I mean, we are going to have like, we will be applying the group theory to molecules, for example. In the case of molecules, the relevant symmetry groups would be a subgroup of this orthogonal group. So if we have a 2-dimensional problem, in that case, the symmetry group would be a finite subgroup of O2. Okay. In that case, we see that there are actually 2 possibilities. One of them is that if the subgroup does not contain any reflections, any improper rotations, in that case, it appears that I can express these groups as it's basically some rotation by rotation angle, which is like 2 pi over n, and its squares and its powers actually, right? So this is 2 pi over n applied 2 times, 3 times, and so on. Okay, and this is essentially a cyclic group, and because of that reason, this group is denoted by C sub n. And then we have the dihedral group. So dn is essentially the symmetric group of a regular n-gon. So I don't know, if this is a pentagon, for example, in that case, we have the ordinary rotations by 2 pi over 5, for example, and its powers as the proper rotations. There are also these reflections in here across these axes. There are also 5 reflections in here. So in general, dn has the dihedral. So this symmetric group is going to be d5. It has 5 rotations and 5 reflections. In general, dn has n rotations, n proper rotations and reflections. Okay, just keep this in mind. So I'm just going to leave that in here. So I'm going to turn this thing off, right? And then share this other one, right? So today and this week, we have actually gone to the 3 dimensions. Our group is O3. So the orthogonal group in 3 dimensions. So in a realistic molecule, of course, the symmetry group of the molecule is just a subgroup of that group. Okay. So again, in here, there are proper rotations, SO3. So these are proper rotations. Basically, these are rotations that are expressed as matrices with determinant +1, and then improper rotations. where the determinant is equal to -1. However, there's some nice feature in here. This is O3 minus SO3. Sorry, I mean the remaining elements in the orthogonal group. So these are improper rotations. The nice thing in here is that there's actually a very special improper rotation, which is the inversion. So it's basically minus identity. So it's just a diagonal matrix where all diagonal entries is equal to -1. So that's inversion. Basically, this is a transformation that transforms the vector to its negative of self. Right? So there's some kind of an inversion involved. So if I have an S is improper, if there's a improper rotation, then that means there is a proper rotation R such that that improper rotation can be expressed as inversion applied after the rotation R, or rotation R applied after the inversion. So the fact that inversion is the negative of identity, so therefore it commutes with all the other matrices, that's an important fact. So because of that, I have these two alternative, these equalities actually. And so therefore I can express any improper as a proper rotation followed by inversion or preceded by inversion. Right? That's an important thing in here. So this kind of enables us to investigate the improper rotations easily. Okay. So once we know something about the proper rotations, we can then easily describe the improper rotations. There's no problem in here. Okay. So as a result, at first, I would like to describe the proper rotation. So suppose let R be proper rotation. Okay. What I do in class is basically by investigating some certain eigenvalue properties of that matrix, then by using them, we say something about the nature of that rotation. Basically, we say that there's some certain axis, which is the rotation axis, and there's a plane which is perpendicular to that. So that proper rotation can be described as a rotation within that plane, right? So the idea is something like that. So, well, R is orthogonal. So that means by using some mathematical properties of orthogonal matrices, I can say that the eigenvalues have modulus 1. I mean, if lambda is an eigenvalue, then the modulus of that eigenvalue is equal to 1. Right? Basically, the eigenvalues, sorry, let me draw this, and as the unit circle on the complex plane, the eigenvalue is somewhere on that unit circle, right? So if that angle is theta, that number in here is equal to e to the I theta. So in general, the eigenvalues have that form. There are two special numbers in here, which are real, so +1 and -1. So these are two possibilities. And then there are these complex numbers as eigenvalues. Second thing is that since R is real, right? If lambda is an eigenvalue, then the complex conjugate of lambda is also an eigenvalue. You can also show that there's actually a way, but I'm not going to repeat this. So that means if this matrix has an eigenvalue e to the I theta, then it also has an eigenvalue which is equal to minus e to the minus I theta. Sorry about that. So let's see. On this complex plane, if lambda is equal to e to the I theta is an eigenvalue, then lambda equals e to the minus I theta is also an eigenvalue. Okay. Finally, there's one thing in here. So the determinant of this matrix is equal to +1, but that's equal to the product of the three eigenvalues. Okay. So as a result, there is also this last restriction on these eigenvalues. So by using this, we can actually say this. So the eigenvalues of R can be, there are three possibilities actually. If it has a complex eigenvalue, then two of the eigenvalues should be complex conjugate pairs, in which case the last eigenvalue should be +1. Okay. Second possibility is that there are two negative eigenvalues. So in that case, one of the eigenvalues should be +1. And finally, the third one is that all the eigenvalues are equal to +1. Okay. In the first case, I can see that the theta is an angle between 0 and pi, 0 and 180 degrees basically, but there's somehow excluding these limits. So it turns out that the second one is just a special case where that angle is equal to pi. And the first one is a special case where it corresponds to the angle being equal to 0. So I can basically think all of these possibilities under a single thing, where theta is actually a value greater than or equal to 0 and less than or equal to pi actually. However, it turns out that, well, this last case corresponds to the identity matrix, because only an identity matrix have identity, or when the orthogonal matrix is an identity matrix, we can have like all three eigenvalues being +1. So if we just exclude these case, we can see that there's actually a single non-degenerate eigenvalue, which is +1. Right? So one eigenvalue of R is equal to +1, right? This implies that there's a corresponding eigenvector. So an eigenvector is basically R applied on n, so it's going to give me lambda times n, but here lambda is +1, so therefore this is equal to n, right? So this is really an eigenvalue equation, but now I'm going to think of this geometrically. So geometrically, n is a vector where after a rotation, it doesn't change. So as a result, we just call n as the rotation axis, right? So that's some kind of a direction which is invariant under this rotation. And so we just call this as the rotation axis. Okay. There's some kind of an ambiguity in here because I can multiply this vector by anything, then I still get the eigenvalue equation satisfied, obviously. I can enforce it to be a unit vector. I can choose it to be a unit vector, but still there's some kind of an ambiguity about the direction, ambiguity. All right, so plus n as well as minus n are possible values of rotation axis, right? There's some kind of an ambiguity in here. So when we talk about a rotation axis, for example, that direction might be the rotation axis or the other one, right? So you may choose this direction as your rotation axis, but somebody else might choose the other direction. So there's some kind of freedom in that. So in any case, what's important in here is that, so that's n is a vector actually. Think about the plane perpendicular to n. So let's just call this P. So P is plane perpendicular to n. Okay. So the idea in here is this. So if I have a vector within that plane, that vector should be perpendicular to n. So because of the fact that the rotation actually preserves the angle, so the rotated vector should also be perpendicular to n, perpendicular to r, and obviously, so that's the same thing as n. So if let's say RV is this thing, right? This is RV, rotated vector. That rotated vector is also within that plane, right? So that means, sorry about that. If V is in the plane, then RV is also within that plane, right? So therefore, R rotates vectors in P to vectors in P. Okay? As a result, I can think of this 3D rotation as a 2D rotation. Okay? There's some kind of an arbitrariness in the choice of that two-dimensional plane, but every three-dimensional rotation is essentially a two-dimensional rotation. So there's actually one parameter involved in here, so that's the rotation angle. There are two parameters involved by the choice of this rotation axis. So in any case, so as a result, two additional parameters are needed to describe this direction here. And so as a result, we need to describe three directions. So let's say it like this: R can be uniquely identified, identified by giving the values of the normal, the rotation axis as a unit vector and the rotation angle theta. So theta is the rotation angle. Okay, rotation angle also has some kind of ambiguity. So plus theta and minus theta, there's an ambiguity also in here. Okay. In any case, we actually remove this ambiguity by using some right-hand rule. So let me describe this, because this is something that I use a lot when we are describing rotations. I'm just going to assume that when the rotation axis is given, we are going to use our right hand. So that's the picture of our right hand. Okay. Let's see. What we are saying is that if n is the direction of our thumb is along the direction of the rotation axis, which we have chosen, then that's the positive direction for theta. Okay. In any case, so if you the ambiguity is still present in here, I can choose the unit vector in the other direction, but it appears that I mean, if I describe a rotation, for example, by using this convention, by the rotation axis and the angle, in that case, the same rotation can be described with the opposite rotation axis with the opposite angle. So as a result, I can pass from one possible representation to the other one. Okay. So as a result, I can then provide a consistent, unambiguous expression for the rotation in here. Okay. So one example is this. So just think about, this is the example. So that's the example that I have given in class as well. So this is the XYZ frame. Just keep in mind that this is a right-handed frame, meaning that if I use my first three fingers of my right hand, so that's the x-axis, y-axis, and the z-axis. So these are basically ordered in the order of the my fingers. I just keep this in mind. So I don't know, if I actually draw some kind of a 3D picture in here, we have something like that, right? Okay, X, Y, Z. In any case, if I have a rotation around the z-axis by 90 degrees, so in that case, that rotation is going to rotate x into y and y into x, right? Something like that. Right? So that's a rotation around z by 90 degrees. Okay. So basically, the rotation axis in here is the unit vector along the z direction, and the angle is plus pi over 2 radians. Just keep in mind that we always use the radian unit for expressing the angles. That's the natural unit, so that becomes important in some certain places. So as a result, I'm going to write pi over 2 radians in here. So if R is a rotation like that, so this rotation basically converts the x-axis into y, y-axis into minus x, well, z-axis, it just leaves the z-axis invariant. If you want to express this as a matrix, in that case, this is going to be that matrix, or the x-axis is converted into the y, y-axis is converted into minus x, so that's the second column in here, and the third column gives you this one in here. Okay. In any case, so this rotation I'm going to describe by the parameters, the z-axis with a pi over 2 rotation. All right, you can check that the right-hand rule is actually gives us these correct angles in here. But I can also describe the same rotation by a rotation around minus z-axis by minus 90 degrees. Why? Well, in that case, sorry about that. So that's x, y, z. How do I describe this in here? So my axis is, well, the rotation axis is minus z. Okay? So if I actually draw the right hand in here, like that, with the thumb pointing down, in which case my other four fingers will be like this, right? So in that case, that's the direction for the positive angles, but the rotation is in the opposite direction. So the rotation is by 90 degrees along this direction. So since it's opposite to my axis of the axis that I had chosen for positive theta, the negative angles will be in here. So as a result, I would basically describe this as rotation around minus c by minus 90 degrees, right? So it's a rotation around plus c by plus 90 degrees is the same thing as a rotation around minus c by minus 90 degrees. In any case, if I have a rotation like that with rotation axis and angle theta, I would actually define a single angle parameter in here, a vector actually, by angle multiplied with the unit vector, all right? So as a result, instead of two different parameters in here, one is a unit vector and the other one is a scalar, I'm going to use just a single vector quantity in here. All right? So that's going to be a nice conversion, because by using this vector, we can actually do lots of different things. So this is a vector whose magnitude gives us the angle of rotation and whose direction gives us the rotation axis. There's still ambiguities in here. So a rotation by 0, for example, 0 vector. So that's the same thing as identity. It's the same thing as a rotation around any axis by 2 pi, or a rotation around any axis by, I don't know, 4 pi and so on, right? So in any case, a rotation by pi over 2 along the z-axis, the rotation above, for example, can actually be described as a rotation by an angle of 5 pi over 2 around z, or it can be described as minus 3 pi over 2 along z, and so on. Okay. Still, I can express the same rotation by different theta vectors. Right? Let's just keep this in mind, because I mean, we don't have one-to-one correspondence between vectors and the rotations in SO3. That's not the case. So the manifold of the rotation group SO3 is somewhat different than the manifold of all possible vectors in 3 dimensions. Right? So SO3 is actually a complicated manifold. So the structure of SO3 is somehow contained in these kind of relations in here. So in any case, we associate many vectors in 3-dimensional space to a single element in SO3. Let's just keep this in mind. Origin is associated with the identity rotation, so that's nice. And we can kind of see that the SO3 is actually connected in here. Okay. I think I need to add this so I can express like any rotation by angle theta as successive application of all rotations by theta over n applied n times. So when n goes to infinity, you can kind of see that this theta over n goes to 0. So basically, you can express the rotation as a successive application of small rotations. So in any case, so by using this, we then prove the argument that the SO3 as a manifold is connected, which kind of says that to do any rotation, I can actually prepare a movie where I start the movie at the location where there is no rotation has been applied first. And then I apply, or continuously rotate this thing, and then finally I get to the final configuration where the final desired target rotation has been obtained. So I can make a continuous movie where the object is continuously rotated from the initial orientation to the final orientation. Okay, so for all proper rotations, I can do this, and that's just a way of proving it. Okay, so there is also a similar theorem in here about the finite subgroups of SO3 or O3. This is slightly more complicated, so as a result, I'm going to come back to this later. I'll just state it later, but it appears that the result is, at least for SO3, for proper rotations, there appears to be the finite subgroups are actually quite similar to the two-dimensional ones that we have obtained, but there are like 3 exceptions corresponding to the Platonic solids, 5 Platonic solids actually. But I'm going to talk about this later. Okay. Next, I'm going to talk about. So from here, I would like to jump to the topic of the symmetry of some certain physical interactions under proper and improper rotation, right? So for this, I need to define this concept of what we call as the pseudovector. So I'm going to, first of all, talk about the cross product, because the concept actually arises from this cross product of 2 vectors. I'm not going to define this cross product again, but let's just think about the situation. So I have a vector A and a vector B. Let's say that theta is the angle between them. Their cross product C, that's A cross B, is a vector which is perpendicular to both of these vectors and whose magnitude is given as, so let's see it like this. So C is A cross B. And we have these 2 statements in here. C is perpendicular to A and C is perpendicular to B, right? And the magnitude of C is equal to the magnitude of A times magnitude of B multiplied with the sine of the angle between them. All right, so whatever. Okay, but when we are defining the direction of C, just saying that C is perpendicular to A and B is not enough, because I have also another vector in here, which is perpendicular to both A and B, but opposite C in here. I have to use right-hand rule, right? Right-hand rule. Okay, in any case, so let's say that R is a proper rotation. And so as a result, I mean, I can think of this as a transformation of the vectors, right? So A is transformed into A prime by a rotation of R, and B is transformed into B prime. Let me do this completely, right? C is transformed into C prime. Sorry, R times C. Okay. If R is a proper rotation, you can see that, well, when you actually look at the angles in here, so A is transformed into A prime, B is transformed into B prime. In that rotation, just notice that the lengths of these vectors remain the same because the rotation is length preserving. It's also angle preserving, so therefore this angle is still going to be the same. Moreover, I'm also transforming the vector C in the same way, so that's C prime. Sorry about that. And these angles are 90 degrees. These angles are 90 degrees. Because the original angles are also 90 degrees, and the length of C prime is going to be the same. Okay. So in that case, you can notice that, well, since C is equal to A cross B, in that case, C prime is equal to A prime cross B prime as well. So the cross product relationship between these vectors is preserved, right? After a rotation, but this is only for a proper rotation. After a rotation, this thing is preserved. Okay. Unfortunately, we don't have this for an improper rotation. So the improper rotation basically changes the right-handedness of your reference frame, actually. So a right-hand rule becomes a left-hand rule, actually. But we don't change the definition of the cross product, so we always use a right-hand rule. So we actually say it like this, right? So let's say it like that. If R is right, this is separate. R is an improper rotation. Improper rotation. So the same thing, right? A and A prime, and they are related in the same way, and so on. So let me not repeat the same thing again. So C prime is also defined in the same way. Let me repeat it, sorry. B is defined in the same way, because that's the part that's confusing people. How do I define the A prime, B prime, and C prime? In that case, if C is equal to A cross B, in that case, under a transformation, C prime would not be equal to A prime cross B prime, but would be actually equal to the negative of that, right? So after an improper rotation, C will be carried to C prime, but that would not be equal to A prime cross B prime. So that's something that we need to keep in mind. Okay. So how do we do this? Well, basically, inversion is an example, right? Inversion. In that case, every vector is transformed into the A prime vector, which is basically J applied on A, that's equal to minus A. So all vectors change sign. So if C is equal to A cross B, right? In that case, A prime cross B prime is, well, that's equal to minus A cross minus B. So that's going to be the same as A cross B, which is C, right? So therefore, A prime cross B prime is not equal to C, it's equal to minus C prime. So therefore, yeah, whatever. I mean, so if I assume that C also changes sign after inversion, just like the A and B, in that case, we won't have this A prime cross B prime would not be equal to C prime, right? So that's the problem that's arising in here. So the reason is that an inversion actually changes the handedness. And so therefore, since we are using the right-hand rule for defining the cross product, because of this change of the handedness, the cross products do not give the same thing when I do the transformation. So as a result, in physics, we have some like quantities that are defined as cross products, like the angular momentum or the torque. So they can be defined like that, and they are defined like that. So as a result, when we talk about the transformation of these quantities, we have to actually understand how these kind of quantities transform under inversion. Right? So basically, we say that there are two kinds of vectors depending on how they transform under inversion. So let's just state this for inversion specifically, and then I'm going to write down how they transform actually under arbitrary rotation in the orthogonal group, right? But I'm just going to specifically talk about the inversion here. So there are these polar vectors. These are ordinary vectors, actually. So let me just say ordinary vectors. Okay, so these are vectors which basically change the sign when I do the inversion. And then there are pseudovectors. So these are also called the axial vectors. I don't know, let's call them like D, for example. They, under an inversion, they actually do not change sign. They remain the same. Okay. So examples of the polar vectors are the position, all right? A position, for example, after an inversion is going to change to a new position, which is equal to minus R. So let's just think of it like this. For example, we have a hydrogen atom, and I have an electron in here, so that's an electron. And this electron is perhaps has some velocity, and well, that's the position in here. Okay. So an inversion. So let's say that the proton is at the origin. Right? So after an inversion, I basically take every particle and then place it at the inverted position. So in the inverted picture, for example, I'm going to place the electron at a location minus R. So that's the new position, R prime, which is equal to minus R. Okay. And let's see, velocity is essentially the time derivative of position. And as a result, this also changes direction under inversion. So as a result, in here, for example, the velocity of the inverted electron would be equal to V prime, which is equal to minus V. Okay. In any case, if that electron follows a path like that, right, let's see it like this, this electron is going to follow an inverted path, right? So I'm just going to take this path in here and do the inversion. I'm going to get an alternate path, and as a result, that's actually that's kind of the transformation of velocity is actually consistent with this. Okay, yeah, and therefore the momentum, which can also be added into that list. So these are basically the vectors that transform in the usual way. The typical vectors under inversion, they are going to transform like that. Okay. Sorry, let me just think about this a little bit. I think I need to add this in here. I do this transformation in my mind. I don't really do this physically because there's no way that you can do this physically, right? For example, you can never take a person and change their right and left hands by doing some kind of a process on it, on that person, because inversion is actually some kind of a it's a discontinuous process, it's a discrete symmetry operation. If you want to imagine something that's inverted, perhaps you can look at a mirror, perhaps. But usually in these kind of situations, we do the inversion like that. We have a particle in here and another particle in here. So there's a negative particle in here, let's say. And the origin is in here, let's say. What we do is like we imagine that a new physical arrangement, for example, where this proton is actually located at the inverted position, and this electron is located at the inverted location. Okay? So basically, I just take imagine that every particle is now at a different location, which is obtained by doing this inversion, right? And this different location is basically is like the position vector. Velocity is the time derivative of the position. So since the position changes sign, velocity changes sign. And momentum is mass times velocity, so therefore momentum also does. Okay. But the angular momentum, so that's basically defined as the cross product of two vectors. So in that case, the angular momentum, for example, doesn't change sign. So it basically remains the same under inversion. And this is quite easy to see. So let's just think about this simple picture again. So the proton is at the origin, and I have an electron in here, and let's suppose that the electron is like in a circular orbit, let's say, right? So in any case, electron is in there, and then it follows this path. Let's see. This gray color, let's just draw this circle in here. It's not really a circle. Let's just try to draw it again. All right. Yeah, it's something like that. In any case, what I do is like, instead of this position, I just consider this inverted position. So that's minus r, and inverted velocity in here, minus v. You can see that in here too, the angular momentum is pointing out of the screen, just like in the original case, right? So the angular momentum in both cases is out of the screen. So when I carry out the inversion operation, the angular momentum did not change direction. Okay, so therefore there are like two different kinds of vectors that transform in these two different kinds of ways under inversion operation. Again, let's remember that the inversion operation is something in our minds. We don't actually carry out physically. That's not possible because every operation that we carry out physically has to be a continuous transformation. This is a discrete operation. No, we cannot do it with physically. Right? We have to do it in our minds, or sometimes people just look at, like, if you have the atom, just think about the mirror image of that atom. But in any case, you're just imagining some kind of an alternative physical situation. Okay. So in that transformation, when we do that transformation, some vectors transform like the ordinary way, right? They change sign under inversion, but some of them they don't, right? So we just call these vectors as pseudovectors. We have lots of pseudovectors in physics. The magnetic field, for example. So the electric field is basically a polar vector, but the magnetic field is a pseudovector. And so as a result, in some certain physical problems, the relationships that we actually obtain between these vectors, they have to be consistent with their nature because of the inversion symmetry of the electromagnetic and gravitational interaction. Okay. And so after this point, I would like to basically describe some of these symmetry arguments. But for now, let's just talk about this. I think I need to say one more thing in here. It turns out that, right, the general rule is something like that. The product of a cross product of a polar vector with a polar vector, two ordinary vectors, is a pseudovector. Okay. Because under inversion, these two change sign, their products do not change sign, so therefore the result is not going to change sign, so therefore the result should be a pseudovector. Sometimes we can take the product of a polar vector with a pseudovector. Right? In this case, the result should be a polar vector. Why? Because this changes sign under inversion, this doesn't, so therefore the result should change sign. Right? You can actually try to think of it like that. And finally, product of two cross-product, actually, pseudovector with another pseudovector has to be a pseudovector. Okay. So we can actually think of these as the rules in here, rules of cross product. Okay. So the next topic is the scalars. So it appears that there are two types of scalars. So one is an ordinary scalar, and the other one is a pseudoscalar. So in any case, an ordinary scalar is basically, it doesn't change sign under inversion. So, and under inversion, it just remains the same. A pseudoscalar, however, is a quantity that changes sign under inversion. So I don't know, let's say this is beta prime that's equal to minus beta, for example, under inversion. So the examples are like these. For example, R dot P is an example of that, right? Under inversion, so let's say it like this. Alpha prime is equal to the product of the inverted vectors in here. So therefore, this is equal to R dot P. So their scalar product, that doesn't change. But in the case of pseudoscalar, so I don't know. In that case, I think I can think of like two particles in here. I can take the position, take the dot product of the position of the second particle with the angular momentum of the first particle. Okay, we can think of it like that. So that's a polar vector and it's a pseudovector, right? One of them changes sign under inversion, the other one doesn't change. So in this situation, beta prime would be equal to the minus R dotted with plus L1. So therefore, that's going to give me minus beta. So that's a quantity that actually changes sign. Okay. Just keep in mind that this is a triple product. So this is the second position of the second particle dotted with position of the first particle crossed with the momentum of the first particle, right? Okay, so we have like the triple product of three vectors together. In a triple product, so these are all polar vectors, so they are going to change sign under inversion. But since there are three vectors in here, the whole quantity, although it's a scalar, it's going to change sign. Okay. We don't have some naturally occurring, frequently used pseudoscalar quantities. Most of the quantities that we know are like scalars, so they don't actually come naturally frequently. But I mean, there might be some specific problems that they might appear. So I mean, especially they appear like that, right? So that's basically they are obtained as a result of a dot product, for example. Okay. So in any case, something that we have to keep in mind. So on Monday, I have just added this. So let me add that as well. We have some kind of a physical system, right? So the physical system is has some certain dynamics, right? I mean, there's some kind of a time-dependent phenomenon. So the particles are moving and the momentums are changing and things like that. Right? The dynamics is described by its Hamiltonian. There's some kind of a mathematical object that's called the Hamiltonian, which somehow captures all the information about the dynamics of that system. Okay. In classical mechanics, Hamiltonian is a function of positions and momenta. In quantum mechanics, it's an operator, right? But somehow, these objects actually capture somehow the dynamics. So we say that a physical system has a symmetry if the Hamiltonian is invariant, right? Physical system has symmetry, let's say G, that's equivalent to saying that H does not change under operations in G, right? So G is a symmetric group, let's say. So we basically express the symmetry of a physical system by the symmetry of its Hamiltonian function or Hamiltonian operator, right? So But to be able to do this, of course, you have to understand how you apply the abstract symmetry operations of that symmetry group to a function like that. Okay? That's something else. We may need to talk about this later. But at least in the context of these scalars and vectors and things like that, we can say this, right? So for O2, for example, O2 symmetry essentially means this. Sorry, it's O3. Sorry, O3 symmetry means this, that H is an ordinary scalar. It's not a vector, obviously, so Hamiltonian is a scalar quantity, but it's actually an ordinary scalar. So that means under inversion, so under rotations, obviously, it doesn't change, but under inversion too, it doesn't change sign. So it's going to remain the same, okay? Which means that inside the Hamiltonian, we cannot have any pseudoscalar expressions. So it cannot, I mean, a typical Hamiltonian can contain expressions like that, r dot p, for example, but it cannot contain expressions like this, r dot the angular moment. Okay. So just keep this in mind. At this point, probably giving examples is not that useful. So as a result, I won't give any examples. But after that point, we have discussed how the electromagnetism obeys this O3 symmetry. The discussion of the rotational symmetry is easy, but we can start with that. But the discussion of how the inversion symmetry can be seen, I have to prepare a separate video for that. So as a result, I'm just going to stop here. So there's going to be some kind of a video about the application of this symmetry ideas to electromagnetism. Okay.